Okay, so subsequent analysis of the orbit of Neptune, again, seemed to show a discrepancy. And so following the same path that was done in the mid-1800s, mathematical physicists looked at the orbit of Neptune and thought, well, there's got to be a ninth planet, which is exerting influence on this seventh planet, or eighth planet, to explain this discrepancy in the position. And Percival Lowell, it's actually the same Percival Lowell who thought he discovered canals on Mars, if you remember. Well, he actually used the same kinds of calculations that the physicists did in the 1800s to predict the location, and the prediction was that it was in a specific location. He didn't actually find it there, but many years after Lowell died, Clyde Tombaugh found Pluto within 6 degrees of the predicted location. So it looks like a repeat of the amazing success that they had in predicting the location of Neptune, which was then discovered in the predicted position, right? It looks like another slam dunk for mathematical physicists who took this tiny discrepancy and figured out what had to be causing it. But, as it says here, it turns out that the problems with the orbits are actually just due to errors in the observations. And there really was no discrepancy. And the discovery of Pluto turns out to be a body that's so low mass, it couldn't have had any effect on the other planets' orbits anyway. So the whole thing was just a coincidence. You almost want to say it's a hoax, but it's like impossible to arrange something like this. But it's just a coincidence, and it just happened to be at the predicted location. It had absolutely nothing to do with the physics of the math of the whole thing. So that's really a pretty mind-blowing coincidence. That's pretty much a 1 in a million chance that you're going to look in a random part of the sky looking for a planet, and it actually turns out to be there just by sheer coincidence. And this is actually the 1978 Discovery photo. Not the Discovery photo. Discovery was in 1930. This is a shot in 1978 taken by the Naval Observatory telescope. And what you see there is not a lot of detail, because this is this is not a CCD image. It's an old photographic image through a moderate-sized telescope. But you do note that there's a blob of emission coming off the side here. Now, this is an unresolved photograph. What that means is that the resolving power here, in angular terms, is comparable to the spacing between Charon and Pluto. So you can't see Charon and Pluto cleanly. It looks like they're merged, but they're really not. It's just an inability to focus properly. So let's see. If I can head to read this. Oh, I had a nice. Okay, never mind. Go back. Thought I had wedged the photo in there that actually showed what they look like, but that comes a little bit later. All right, so looking at Pluto's orbit, a very large eccentricity, 0.25, the largest eccentricity of any planet around our sun. So what you see is a percentage variation in distance from the sun of 50%, the largest variation. And look at the whopping change between perihelion and aphelion. Quite a difference. Sorry, the sound effect there. Quite a large variation. In fact, if you happen to remember what Neptune's aphelion distance was, it was pretty close to that perihelion distance, so we'll talk about that. All right, so we use Kepler's third law now, stick in the semi-major axis of 39.4 astronomical units, and you get 248 Earth years. So a full 248 Earth years for the orbit, one single orbit of Pluto. So it's only completed about a third of an orbit since it was discovered. All right, so just following up on what I said a moment ago, if you compare that perihelion distance of Pluto, the one at the top there, closest approach to the sun, and you compare it with the aphelion distance of Neptune, you see that it's possible for Pluto to actually be closer to the sun than Neptune is during part of its orbit. So we think that this may actually indicate that Pluto itself may be an escaped moon from Neptune. It's very similar to some of the moons of Neptune that we looked at. Very icy composition, very similar density. It may be that because of the influence of another body, which is now gone, Pluto may have actually originally been a moon of Neptune, which was wedged away by another intervening body's gravitational force. And so here's just a diagram that shows you how Pluto in 1989 was actually closer to the sun than Neptune was in 1989. So clearly a fan of of bare metal. And that's what they. Right, well, it turns out that if you look at the actual, well, I mean, this diagram, it looks like they almost could collide or something like that. But there's another factor here, which is like the third dimension coming out. It turns out the planes are tilted with respect to each other, so they actually don't get all that close together. And it doesn't totally explain what's going on, but they get close enough that if another body had intervened, you know, you might have been able to achieve this, but we don't think there's any chance of them actually colliding or anything like that when you take the tilted to consideration. Okay, so anyway, to go a little bit further with this, you know, we're always interested in this question of is there a relationship between orbits? We've just shown that Neptune's orbit is 164 Earth years and Pluto's is 248 Earth years. If you do the math there, every 2 orbits of Pluto is 3 orbits of Neptune. So it's actually possible that there's a 2 to 3 resonance between these bodies, which is due to the fact that they do make a relatively close approach every 300 years. They actually don't get close enough to collide, but they do get close enough to interact gravitationally. And there may actually be an effect going on here of that type. Because when we see integer ratios like that, we figure it's not just a coincidence. All right, so bulk properties, probably not worth going through all of the numbers here, but the bottom line is that when we divide the total mass by the total volume, we get these density figures. Neptune and Uranus, again, gaseous planets, Pluto, around 2 grams per cubic centimeter with a predominantly icy composition. So let's look inside these bodies. Now we've actually already talked about the interiors of Jupiter and Saturn, and Jupiter and Saturn both have a molecular hydrogen outer layer, which is H2. Then they have a layer below that, which is a higher temperature and pressure, which is metallic hydrogen. And again, that's a phase of hydrogen that doesn't really exist under earthly conditions because you're talking about thousands of kelvins and thousands of pressures, atmospheres of pressure. But the metallic hydrogen layer is very important because it's where you can get the electrical currents that can help form the magnetic field. Now when we look at Uranus and Neptune, at their distance from the Sun, we actually don't have the conditions that would lead to the formation of metallic hydrogen phase. So we think that below the molecular hydrogen layer, in the case of Uranus and Neptune, there's a different kind of material that we haven't encountered before, which is actually a kind of ionized ammonia, semi-frozen slushy material. The fact that it's ionized, again, means that there's 3 charges which can form an electrical current. So this ammonia slush, as we call it, we think is the part of Uranus and Neptune which is able to circulate as the planet spins, creating the electrical currents that would give rise to magnetic fields. Okay, so when we look at the equilibrium temperatures, when we get as far out as Pluto, the surface temperature is only 50 kelvin, which is the equilibrium temperature out that far. So there's no funny energy source inside Pluto. But only 50 kelvins. Now remember that 0 kelvins is absolute zero, the complete absence of molecular motion. So this is just unbelievably cold out there now. It's so cold that, again, you're seeing cycles of methane freezing and thawing. In fact, as we'll see, because of the variation of Pluto's distance from the Sun, there can actually be methane seasons. You can have seasons where you have methane snow, seasons where you have methane rain, because the difference in distance from the Sun takes you in and out of the temperature range where methane freezes. Okay, so rotation rates, the main point here is that we're still seeing pretty quick rotations, faster than the Earth value of 24 hours, right? See 17.2 hours for Uranus, 16.1 for Neptune, similar to the thin periods of Jupiter and Saturn. And so we're seeing pretty strong magnetic fields, which I think is because we have the 2 ingredients that we need. We have a way to have electrical currents, which is this ammonia slush, and we have rapid spin, right? So those are the 2 ingredients we need for strong magnetic field. We have those in the case of Jupiter and Saturn too, because Jupiter and Saturn spin with a period of about 10 hours, even faster than these guys, and Jupiter and Saturn have the not magnetic, but the metallic hydrogen, which is again that layer where you can get the current. And then Pluto with a spin period of 6.4 Earth days turns out to actually be tightly locked with its moon Charon. Now, Uranus is tilted over in this weird way, which means that seasons on that planet are very extreme. We think this is probably the result of a collision. This is another example where we appeal to a collision to explain the breakdown of the general pattern that we've seen through the whole solar system, which is that the spin axes all point to the north celestial pole, more or less. The only other exception we've seen to this before this point was Venus, which is flipped over like almost 180 degrees, and Uranus is kind of tilted over on its side. So we're going to see extreme seasons because when it's summer in the southern hemisphere, it's going to be a complete deep freeze in the northern hemisphere. Very extreme seasons without any sunlight at all. Okay, so we need to talk a little bit more about the atmospheric composition of Uranus and Neptune to understand why they have this bluish color. You know, I mean, they don't look like Jupiter and Saturn, but they're all gas giants that probably formed with the same primordial compositions. And when we look at Uranus's atmosphere, we're actually seeing pretty much the same composition that we see when we look at Jupiter. The primordial composition, about 85–86% hydrogen, around 14% helium, traces of other things. Now, we believe that these two planets are displaying the primordial composition at the cloud tops. By the way, remember that these abundances we're talking about are at the cloud tops because we don't have any inner knowledge of these planets, right? We just look at the cloud tops. But we think that these actually do represent the complete composition of the planet through and through because at this distance from the sun, we don't think we're going to get any kind of differentiation of the composition. The cloud top temperatures on Uranus and Neptune, around 60 kelvins, are, again, the expected equilibrium temperatures, a little warmer than what we see when we look at Pluto. Okay, so as to the bluish color, what we're actually seeing is a buildup of methane gas. We're starting to see a little more methane gas, CH4, in the outermost planets than we're seeing in Jupiter and Saturn. You see over there it says CH4 is 2%. 2% of the atmosphere of Uranus is methane. It's only a trace element, much less than 1% when we look at Jupiter. Methane tends to absorb red light, giving the planet this bluish appearance. So as we move out into Neptune, we actually see a bump up of that number to 3%. 3% methane. So we see an even deeper blue color when we're looking at Neptune. And again, this is another example of differentiation in the solar system. Because methane gas is a very light gas, it tends to be farther from the sun. So there is Uranus, very featureless. If we look at Hubble photos that are enhanced, we can see sort of some clouds and things. Not too much going on there. Neptune actually has a little bit more of atmospheric variation, and we can see some storms. Now remember that the differences here are that Uranus is closer to the sun than Neptune is, but it's got that weird tilt, remember, that crazy tilt. We think that crazy tilt is actually kind of impeding the general ability of the atmosphere to circulate locally because you don't see much of a daily variation. But we do when we look at Neptune, so that might help explain the larger variation we see in the clouds when we look at Neptune. We do see evolution on pretty short time scales, kind of similar to what we saw in the case of Jupiter, where the cloud structure can evolve as materials flow around and we get chemical reactions taking place. And again, wispy clouds, probably frozen methane crystals in the upper atmosphere of Neptune.